We have already designed the up counters and down counters separately in the previous presentations. In this lecture, I will teach you how to have a 3-bit and 4-bit up-down ripple counters. This ripple is for asynchronous counters. The clock is not simultaneous to all the flip-flops. And up-down means this counter that we are going to design can count up as well as it will count down. So it is a very important presentation because in practice both these modes are combined. The down counting and the up counting are not separate, but there is a common circuit for it, and depending upon the mode control input M used to select the up or down mode, this mode control input will decide whether the circuit, whether the counter will do the up counting or it will do the down counting. So we require a combinational circuit between each pair of flip-flops. That's why I have left some space here, and we have to find out the combinational circuit that we have to use in order to select QA or QA complement, which will be given to the clock of the next flip-flop, that is my B flip-flop. In the same way, we will use the same combinational circuit which will decide whether QB or QB complement is to be given as the clock. So this is our aim in this presentation. We have to design a combinational circuit in which the input is Q complement and M. This M is the mode control input. Q and Q complement is the output of previous flip-flop, and this Y, the output of this combinational circuit, is given to the next flip-flop. So the first thing that we have to do is to find out this combinational circuit. Then we will insert this combinational circuit between the pair of the flip-flops and our job is done. So I will make one table for this purpose. So let's make it. The first input is M, the mode control input, then Q, and then Q complement. As there are 3 inputs, definitely we have 8 possible combinations. So let's write all the possible combinations. 0 1 0 1 0, then 0 1 1. Then we have the next 4 combinations as 1 0 0 1 0 1 1 1 0, and then 1 1 1. These are the 8 possible combinations. Now how we can decide the output Y? What is the logic? We have to first set some logic, then we have to find the Y. So I am telling you that whenever the value of M is equal to 0, it will do the up counting. It will do the up counting, and whenever the value of M is equal to 1 or it is high, it will do the down counting. So this is what I have decided, and we will use this logic in our table, and finally we will have a K map and our combinational circuit. So I can say whenever M is 0, Q is connected to clock of the next flip-flop, and whenever we have M equal to 1, it means down counting. Q complement is connected to the clock of the next flip-flop. So let's try to have the values of my output Y. M is 0 for the first 4 cases, and when M is 0, you can see up counting, and we already know there is up counting only when Q is connected to the clock. So I will write Q as my output 0 0 1 1, because this Y will act as the clock for the next flip-flop, and when M is equal to 1, it will do the down counting, and Q complement is equal to my Y. And for the last 4 cases, M is equal to 1, so I have to take Q complement, that is 0 1 0 1. So we have our output. Now we can easily have a 8-cell K map, and we can have the function Y, which is minimized. So I will make a 8-cell K map, and the inputs are M, Q, Q complement. M is the MSB, so we have to write M here. Q complement is the LSB, so we have to write it here. So 0 1 0 0 0 1 1 1 1 0. Now let's fill this K map, then we will do the pairing 0 0 1 1. So 0 0 1 1, then we have 0 1 0 1, So 0 1 0 1, a very simple K map. We have two pairs, the first one is this and the second one is this. Let's call it 1 and then 2. So the function y is equal to 1 or 2. We will first find out 1, and it gives us m complement, and we have q, because q complement is changing from 1 to 0. So m complement q, or let's find out for the second pair. We have m, because m is 1 for this row, and then q is changing from 0 to 1, so it is 1 and we will not write it in our function, and q complement is 1, so I will write q complement. So our y is equal to m complement and q, or m and q complement. Now we will implement this logic in between our flip-flops. So let's do it. First of all, we have to make a control input. So I will write m here, and I will use a NOT gate that will give us m complement. So let's first make it. Then we will use AND and OR gate to implement the obtained logic. This will give me m and this will give me m complement. Now we have the first minterm as m complement q, so I will use a AND gate here. This is my AND gate, and for the second minterm also I will use a 2 input AND gate. Okay, and this is m complement q, so I will give q and m complement. Now we will implement the second minterm. It is m q complement, so q complement, and then we have m. So this AND gate is giving me qa m complement, and this AND gate is giving me qa complement m. So the last thing that we have to do is to use a OR gate. I am using OR gate, 2 input OR gate, and this OR gate will go to the clock of the next flip-flop, and the input are the output of this 2 AND gate. So here I am having the function y, and y we have to feed this y to the clock of the next flip-flop, and the same thing I am doing here. So this is the logic that will decide whether we have to do the up counting or the down counting. In the same way, we have to implement this logic here also. So let me do it quickly, then we will see what is happening depending upon the value of m. 2 AND gates are required and 1 OR gate is required. This is a 3-bit up down asynchronous counter because I am using 3 flip-flops. If you want a 4-bit up down asynchronous counter, you have to use 4 flip-flops in the same way. So you will use another flip-flop here, and you have to implement this combinational logic once more, but now we have to implement it only 2 times. So this is QB, and then we have m complement. So here I am having QB m complement. This is QB complement, and we have to give m here. So I am having QB m, and the output of this OR gate is fed to the clock of the next flip-flop. So this is a complete circuit diagram for your 3-bit asynchronous up-down counter. Now let's see when m is equal to 1. When m is 1, it means here I am having 1, whereas here I am having a 0. So this AND gate will give me 0 because it is m complement qa, so it is 0, and this AND gate will give me qa complement, and 0 or qa complement is definitely equal to qa complement. So the qa complement is given as the clock to the next flip-flop, and definitely it is down counting. And here also I am having 1 and a 0, so this is equal to 0 and this is equal to QB. This is QB complement, and again you can see QB complement is fed as the clock to the next flip-flop, and it is down counting. And I have already written here, when m is equal to 1 it will perform the down counting, and when m is equal to 0 it will perform up counting. You can check whether it is performing up counting or not. You have to only replace this 1 by 0 and this 0 by 1, and again this is 0 and then 1, you will find that QA is fed as the input to the next flip-flop and QB is fed as the input to the next flip-flop, and we have the up counting. So this is all that you have to keep in your mind regarding the up down counter, and this is a very important topic because in the same circuit you are having the up as well as down counting. So I think this is all for this presentation. See you in the next one.